Welcome to ESIG. If that's your first day here, we had an opening sessions yesterday, but I know some people just arrived today. So we are starting our first parallel session today. So you're in a session 1A on grid forming inverters. So if you're intended to be in session 1B, it's in the next room. And so this this session is chaired by Unruh, who's Vice President of Electranix, and I'll give it over to him.
Good morning, everyone. My name is Andrew Isaacs, as Julia said. I work for a consulting company called Electranix, based in Winnipeg in Canada, which is, just by the way, I need to just mention that our hockey team in Winnipeg is first in the NHL league, all 32 teams. So I know you're all very excited and cheering for the Jets this year. It's going to be a good year. Welcome to this morning's session on grid forming inverters. Or I should say converters, if you've been around power systems in the last few years, you'll have certainly heard about grid forming. It's been a popular topic, but I wanted to just give a quick couple minutes reminder about what we're talking about if you haven't heard about grid forming or if you're not sure exactly what we mean by that. So conventional inverter-based resources, or IBRs, such as wind and PV and batteries and HVDC and all of those other things, have classically relied on the presence of spinning synchronous machines to provide a strong reference for their controls. These IBR controls need to synchronize tightly to this reference, and we call them grid following as a result, and they may struggle to effectively control themselves as the synchronous machines are replaced in our grid with more IBRs. So more recently, IBRs, and in particular battery systems, have been made available with alternate control philosophies, okay? That we don't rely so much on the presence of these synchronous machines for stable control, but are able to synchronize with each other and with the external grid. We call these grid forming. And they have the capability for an expanded range of services and benefits and new applications. So in the past few years, this technology has become much better understood. Many regions are actively designing requirements and reorganizing their service markets to take advantage of the technology. So there's lots of projects now in active service, and we think that in the next few years, we will likely begin to see much more widespread adoption. So we're kind of over the hump, I think, and we're going to be moving into a new sort of world where grid forming is not so strange and new. There's a lot of great resources out there to help you further understand how grid forming works, the basics of it, what it's good for, how to specify it, and so on. And not least of these are provided by ESIG. So I would direct you to the ESIG website. There's Julia's put together a lot of excellent sort of compilations of resources. There's papers, videos, lists of resources, and so on. We have a very diverse panel today. We have consultants, utilities, researchers, and manufacturers. Our speakers will touch on a really wide range of topics. You can see from the schedule, we've got tons of different topics we're going to talk about in just under 2 hours. We're going to include emerging applications and benefits, standards and requirements, and how do we test it, and some of the lessons learned. We're going to work hard to leave some time at the end for questions. So without further ado, I'd like to introduce our first panelist, which is Sam Maleki. Sam is a director of T&D Engineering and Consulting at RMS Energy. Let's give him a round of applause, and we'll hold questions till the end.
Good morning, everyone. My name is Sam Maleki, Director of T&D Consulting at RMS Energy. It's 8 a.m., a little bit too early, but I'm trying to catch. Anyway, for today's presentation, I'm going to discuss about like the challenges of AI-based data centers and how grid forming actually can help us to tackle a couple of these challenges. So AI data centers behavior, I think it was a discussion yesterday that there's a huge difference between the conventional data centers and the AI-based data centers. We see power quality issues, we see right-through issues and everything around that. So one of the potential promising way to tackle these challenges, we found out it could be grid forming, and that's what we are going to discuss today. So as an introduction, one of the questions that I get from time to time is that if AI data centers are challenging and we are seeing the issue now, why we haven't thought about it a couple of years ago? Why not 2 years ago? Why there's no paper around it? I mean, if you look at the IEEE, CGRE, and ESIG, we don't have the information. We don't have good papers to show that, okay, these are the issues, these are the mitigation. The answer to that is that they never existed before, or they never existed with these huge, large hyperscaler sizes. We had data centers of 50 megawatt, let's say 100 megawatt, but the majority of them were used for cloud computing, storage, not for AI purposes. One of the challenges for these AI-based data centers is the power quality. By power quality, it means it is already observed that 2-3 years ago, when ChatGPT came into the market, around the same neighborhood of the existing data centers facility, people start seeing their lights goes like flickering on and off thing. It was that time that people realized that there's something is off in terms of the computation of algorithm for AI-based data centers. So if you run crypto mining, if you just have the facility to store data, typically the consumption is constant, so you don't see that much of variation. For AI-based data centers, it's different. It depends on the algorithm. The power can swing drastically. So I had a call yesterday that a 200 megawatt facility can oscillate with like 50 megawatt up and down very quickly. So one of the solutions is grid forming. Why grid forming and everything around that? We get to that. Let's talk about the data centers in the fundamental of data centers. So there are different tiers for data centers, tier 1, 2, 3, and 4. Each tier has its own reliability and resiliency. The tier 4 can provide the maximum reliability, resiliency, and everything. What does it mean? It means that the data centers wants to connect to your network, but they want to have the most beautiful power ever. Like the voltage should be perfect, the system needs to be perfect, then I can stay with you, with the network. Anything happen to you, I have my backup generator. I switch back to my local supply. If you talk to the data centers developer or the owner, what they say is that, yes, we have the fault right through, but it's actually wrong. The conception of the fault right through, they look at it as the load perspective, not the grid perspective. So yes, anything happens to the system, I switch to the local mode, I write through the fault, I can still do my AI thing, but I don't care about your network. So now imagine like 500 megawatt just go away. It was a point of discussion yesterday. So the fault right through is one of the key elements of the challenges of data centers. There's other aspect of it, why they need that much reliable power. So I just asked ChatGPT, what's the financial, like the revenue losses or the losses that they can get it's huge. Like for 1 hour of outage of these data centers, they can, the losses that they can expect is up like 5 million to 10 millions of dollars. I'm not talking about the lawsuits and everything. So these are critical infrastructure. They have to be in service. So they have their own purpose of, yeah, whatever happens, I go out, I supply locally, because there's millions of dollars revenue loss for each and every hour. Talking about the grid forming, and this session is about grid forming. Grid forming has the beauty of provide additional support to these data centers. So in this study, what we did, we used the IEEE 9-bus system, very small network, but actually can give us a lot of good insight. We had 500 megawatt data centers connected to this facility, and we added a grid forming inverter beside it. Some people asked that where we should add the grid forming. Is it like at the point of interconnection, or I can have it somewhere in some other places in the network? I can answer to that question. Or a study showed that if you want to think about grid forming, if you want to think about ES.com or anything like that, we actually need it right at that POI. If you put it somewhere else in the system, it's not going to work that well. The correct answer is that even not the POI, is on the medium voltage side. So with the grid forming technology, we developed the data center. Actually, we developed the data centers in detail. We didn't have it before. It took us sometimes basically to talk to a couple of the OEMs. The problem was the data. We couldn't get the data, how exactly they behave, how to model a UPS system, what is the cooling motors look like, what's the share of them. So we try to gather all those data. We come up with a good setup in PSCAD software for the data centers, and we added that grid forming. This is the structure of the controller. I'm not going too much into the detail of the grid forming, control it, algorithm and everything, but let me go here. Okay, couple of results. So if we don't have the grid forming, if we just want to put the data centers connected to the network, there are two scenarios that can happen. Either they write through or they cannot write through the fault. So if you look at the results, if they don't write through, you see that there's a huge voltage sag. That's the red one, I think. If they write through, then you see high voltage issue. So some people are saying that, oh, we need to provide write through these data centers, then everything is okay. Because of the induction motors and other elements and the UPS technology, it's not only about write through or not write through. Both of them has the same issue, kind of. Either low voltage or high voltage issue. So there's a definite need for some other element to make sure to come into place and actually help us to provide the better write through criteria. And that's the grid forming. Or ES.com. I'm not just saying that grid forming, but grid forming is one of the solutions here. If you look at the blue curve here, then you see that, okay, this is type of a write through that I'm looking for. I don't want to see overshoot of the voltage. I don't want to see under voltage and anything like that. So grid forming can beautifully provide that voltage support and actually write through. One of the reasons that I'm saying that it's better to have the grid forming on the medium voltage side is basically the fact that all those UPS devices, they do not want to see the voltage fluctuation. So that's the best place to fix everything on the medium voltage rather than the high voltage. The other study that we did, actually, this is for the write through again. As you know, if they don't write through, the frequency of the network can go up. It happened in our system. 1.5 gigawatt of the data centers goes out, the frequency jumps. It took 12 minutes to bring it back down. So Again, grid forming can provide that service to the data centers facility. This one is the interesting one. The AI data centers, as I said, the voltage, the power consumption can jump up and down depending on the algorithm. And it's kind of random, or there's something behind it that we don't know how it behaves. But in terms of 100 to 200 milliseconds, they can jump from 30% to 80% and comes back down. What will happen here, there's a huge amount of flicker and harmonic. So there are discussion about co-location or on-site generation. Some people talking about a huge nuclear facility or huge generator units that can supply. Sure. What actually happens is that it's not going to work. Look at it this way. If I have a huge generator facility, let's say 500 megawatt of generator, huge one or a couple of them, and I put it beside a 500 megawatt of AI data center, so still I have those up and down, the peaks, right? That energy needs to go somewhere. Either it goes to the grid or it goes to your generator. And all these generator has the mechanical shaft, multi-mass shaft. We did this study and we noticed that after some time, that shaft will break. Because what happens here is that those up and downs, it will wobble the shaft. So the shaft starts, you hear it, and there's also protection of that unit. Either you need to bypass that protection and just let it do the back and forth thing, and eventually it will break. So generator is not the solution to tackle this one. What we found out is that grid forming is the solution. So grid forming technology can actually work perfectly here. It can reduce the flicker drastically. So this is the first voltage that you see here is without grid forming. The second one is with the grid forming, and you see that it's a good thing. And this is the final results for this one. The flicker was so high, so I don't think even they can connect to the grid, but if you pair it with the grid forming technology, then actually you can reduce the flicker drastically. And yes, if you're talking about the lifetime of it, I think there's an effect on the lifetime of the energy storage for sure because of the speed of the charge and discharge, but that's one of the solution. Yeah, all right, so this is kind of my last slide. I had this slide like 2 years ago in another ESIG event in Arizona. So what this picture shows us is that for many, many years, we tried to train our generators to supply the load. So loads were just relaxed. Loads were like, just give me the power should be good, reliable, resiliency, and everything around that. I think we are not in that time anymore. The time has changed. These loads are becoming even much, much more bigger than the generator. So their effect is much more than the generator units. I think this is the time to ask for the loads to provide all beautiful services, ancillary services, frequency support, and everything around that. I don't have those results here, but we actually show that you can get a lot of good benefits from the load side, even if your generator is intact. You can get the power system reliability, resiliency, and everything. But we need to train these loads. We don't know UPS yet. We don't know AI data centers yet. But what we know and we studied is grid forming. I think there are a lot of people in this room and unstable that actually work with grid forming technology. So let's use that technology to make sure that we pair them with these loads and go with this transition. That's pretty much from me, and thank you so much.
Thank you, Sam. Next, I want to introduce Hossein Ashourian, Power System Modeling and Simulation Specialist at EMTP. Let's give him a round of applause, please.
Good. Hello, everyone. Good morning. This is Hossein from EMTP, and today I want to talk about the performance requirement for the grid forming. Because of the time limit, I skip the first 3 slides and directly go to the case studies I want to present for you. The first case study I want to present is, we call it unit testing for the grid forming, is loss of the synchronous machines and discharging. This test is designed for the battery energy storage grid forming only. And you can see in this test, we connect the 2 grid forming to the synchronous machines. And then at some point, we disconnect the synchronous machine and we see the performance of the grid forming. So one of the grid forming, we call it the grid forming on the test. And another grid forming, we call it duplicate grid forming, but the half rate of the first grid forming. So you can see after disconnection or power loss of the how the grid forming performed to this power loss. Both of the grid forming directly reply to this power loss, increase the power, and also the voltage, the grid voltage reduce, drop, and then back to the steady state based on the group voltage you define. So this is the grid frequency performance. So we have several challenging for this test. We have to check several challenging for this test. One of them, the first one is the voltage source behavior of the grid forming. So the voltage source behavior of the grid forming means that during the islanding, the grid forming should regulate voltage and frequency of the grids. So we have also oscillation damping. As Sam mentioned, one of the applications for the grid forming is damping the oscillation. So the second case study I want to present is to check the grid forming performance during the different short cycle levels. So the grid forming here is connected to the equivalent network. So we try to change the short cycle level and apply the faults. The fault we apply here is the two phase to ground fault. And you can see here, we try to reduce the short cycle level and applying the fault. So here you can see how the grid forming reply to this short cycle level. And the grid forming in this case should operate robustly during the weak grids. And you will see that grid forming operate correctly. So the next test I want to present to you is the performance of the grid forming during the unbalanced conditions. So this is very important because one of the idea is to replace the grid forming with the synchronous machine. So how the grid forming performed in this case? The case study here is very simple case study. We have an external grid forming, and the local loads. At some point, we disconnect the external grid, so the grid forming become islanded with the local load, and then we apply unbalanced fault. We want to see the performance of the grid forming during this condition. You will see during this condition, the performance is similar to the synchronous machine. It's not exactly the same, but it's similar. So you don't have hour voltages, similar to the grid for the synchronous machine is inductive performance. And also you can inject reactive current, negative sequence reactive current to the grids in order to control the hour voltages. So this is the performance of the grid forming in this case depend on the controller type. So we call it the decoupled control. We have coupled control, decoupled control. So decoupled control, you are able to regulate the negative sequence current injection through the fault. So another case study is the performance of the grid forming with the series compensated transmission line, which is a very normal case in this, the power system studies. So here is a Hydro-Quebec test. It's a very complicated test. It includes several wind turbines, PVs, synchronous condenser, HVDC, and etc. And then one of the wind turbine connected to the grid through the series capacitance. Let's go to the results. At 5 seconds, we add the series capacitance. So you can see the wind turbine output power is oscillate. So we have oscillation in the wind in this case. So we replace the wind turbine. We replace the wind turbine with the same rate and the same initial condition. And then we'll see that the grid forming can help stabilize the system. So actually the grid forming damp the oscillation. So one of the application in this case for the grid forming is damping the oscillation due to the series capacitance. So another case study I would like to discuss is the performance of the protection system due to the grid forming. So we have in this case study, we have 4 synchronous machine and it's connected to the equivalent network to the transmission line. We have a parallel transmission line. We apply fault in the top lines and then we disconnect the line and you will see how the impedance change seen by one of the relay from the bottom line. Actually, you can see here, the impedance goes to the swing, the area, the first zone, around 3 cycles. Now we replace 2 of the synchronous machine with the grid forming, and we want to see how the impedance change during these conditions. So you will see the impedance change similar to the grid, similar to the synchronous machine. But here you can see this, the grid, the impedance go to the zoom of the power swing, the upper zoom of the power swing after 5 cycles. This means that if you want to replace the grid forming with the synchronous machine, you have to check the protection of the system. And this is very important. You cannot simply replace it, the grid forming with the synchronous machine and the system is work. So you have to do protection coordination again and check all of the protection. So let's go to the integration of the grid forming in the large grids. So I select 2 case study here. One of the case study is Chilean grid network. So we have a lot of challenging for the modeling of the large grid. One of the challenging is initialization. During the simulation, you have a lot of power renewables connected to the large grid. And if you are not able to initialize the grid correctly, you are not able to run it. You have a lot of problem at the beginning. I don't know if you face this problem for the modeling of the large grid or not. We have also control interaction. You have a lot of renewable connected to the grid, and all of the renewable interact together. So you have a control interaction. Another challenge is placement of the grid forming. So let's say you have a large grid and you want to place some grid forming to the grid. At which place you have to place it, and what are the size you have to add it to the grid? I will skip this one. You will see also the initialization of these large grids. So in EMTP, we have load flow. So we initialize all of the component from the load flow solution, and you will see you don't have any issue from the beginning. So you can apply perturbation or fault at 1 second. You don't need to wait a long time to apply the fault. So let's discuss about some cases here I added here. The first case, I call it the base case. We don't have a grid forming in this case, 70% penetration of the grid following, and we apply 2-phase fault at the 500 kV substation. So you can see after clearing the fault, we have the system become unstable. Is it similar to the similar blackout happened to the Chilean network 2 weeks ago? So when the system, they apply the protection system doesn't work. So after that, the network become islanded and 2 parts of the network, become unstable. So we replace after that, we replace 4 grid following converters with the 4 grid forming inverters, battery energy storage actually. And then you will see for this case, the system is stable. So the grid forming helped to system become stable in this case. Another case we did is islanding events. So when you apply fault in the transmission line in the 500 kV, and after that, the complete transmission line disconnected. So we have two parts of the island network. So you can see also in this case, the grid forming helped the system become stable. So the next case study for the integration of the grid forming to large grid is the Wake 240 bus systems. Is a very large system actually. And the test we did here, we just replaced the 5 synchronous generators, 14.9 gigavolt ampere with the 5 battery energy storage grid forming inverter with the same rate and same initial conditions. After that, we create the events. The event we create here is power loss. So we disconnect 7 power plants, totally 17.7 gigavolt ampere at this area. So let's see what happened after this power loss. So is a little bit interesting. You will see also the grid forming number 1, which is very close to the event, this one, to the power loss, respond very fast and quickly. The other grid forming is grid forming number 3, also is fast quickly, but the other grid forming you can see is not fasting, is not react very fast. It's react, but is based on the droop and inertia. So the sizing and placement of the grid forming also is very important, the very large grids. So as a conclusion, what I can say is efficient and accurate model can be developed in EMTs, type simulation, but you need to do model validation and check the model quality. So the model validation, what you can do from the first step, you can validate your model with the phasor domains, the model you receive. After that, real-time simulation and etc. So you have to do a lot of tests to check the performance of the grid forming. We defined several tests in this presentation, but you can add also more tests to understand the performance of the grid forming. Actually, the grid forming model you receive from the OEM is a black box model. So you have to perform a lot of tests to understand the performance of this model. We check that for the large grid, the grid forming can positively impact on the grid stabilities. And also we need some benchmark to test all of this performance. That's it.
Thank you very much, Hossein. Next, we have a presentation by 2 folks from Tesla. Ali Mohammadpour is a staff power systems engineer, and Sarah Walinga is a staff power control engineer at Tesla. Thank you. I guess you guys will share.
All right. Good morning, everybody. Today, myself and Sarah will be talking about Tesla megapack grid forming and including how the architecture is and also lessons learned from the operational grid forming throughout the world. First, let's look at Tesla grid forming approach. In Tesla grid forming or megapack, the grid forming operates as a standalone voltage frequency source, which contains 2 main paths, including the power dispatcher and virtual machine. In the power dispatcher path, you can set the real and reactive power set point from a Tesla site controller, which is actually the equal to power plant controller. And the virtual machine path, which operates as a rotating machine, is a voltage source behind an impedance which responds to the voltage and frequency references received from the power plant controller. And this is done through the exciter models and the swing equation models similar to that of the synchronous machine. So in general, in Tesla grid forming, the inverters respond to based on a sub-cycle basis to maintain the voltage and frequency references received from the Tesla side controller. Like in summary, in the power dispatcher path, which actually acts on the left-hand side in the picture as a current source, things like peak active and reactive power dispatch, frequency market, plant level voltage control, etc., can be achieved. On the other hand, in the virtual machine path, which is similar, which acts as a rotating machine, things like inertia power responses, phase jump power responses, and also black starting and things like increasing the system efficiency can be achieved. As mentioned, in the Tesla grid forming dispatch, dispatch can be achieved in two ways. We can either manipulate the voltage and frequency received from the Tesla side controller to the virtual machine, which is something that is like, traditionally done by other grid forming approach. But in Tesla grid forming approach, what it makes is unique is that the direct power command can be dispatched directly to the machine, which actually brings several advantages, including it provides less complexity for the secondary controller because the need for reverse loop calculation and slope calculation and coordination can be reduced. Also, since the machine current in this approach is in the steady state is 0, which means that the machine is not loaded, the machine initializes at the load angle of 0, which means that the load angle stability and transient stability of the machine can be improved in the Tesla grid forming. Overall, as you can see in this figure, we have the frequency reference, voltage reference, power and reactive power reference sent to the Tesla side controller, where the output is the P command and Q command to the dispatcher at the top dispatcher path, and also the frequency reference and voltage reference will be passed through the virtual machine path, where at the dispatcher path we're going to have, based on the P and Q dispatched, the current will be calculated. And in the virtual machine path, based on the using the swing equation exciter, the voltage source, the voltage of the voltage source will be calculated. And as you can see, since the current in the is separated from the synchronous machine, visual synchronous machine, the steady state current of the machine is 0. Which in the next slide, I'll show what advantages that this brings. So with the Tesla Megapacks, both transient and steady state response management is possible. Here in this slide, you can see step by step what happens within the Tesla grid forming once a grid event like loss of a big generator happens. At when we lose let's say, a big generation plant, the frequency drops suddenly sharply, and at this point, the inverter's inertia and droop pushes the power beyond the operational limit of the power temporarily for a few seconds, and then the reference value at the machine level are refreshed in order to make the reference value equal to the real actual frequency of the grid. And at this point, the machine response goes away because now frequency reference is set to the actual frequency. So the machine response stops. And at this point, the inverter's droop and inertia power is cleared. But at this point, the side level droop becomes effective. But at this time, it is actually limited to the operator's limit. It cannot pass the operator limits until at the final step, the grid operator redispatches and rebalances the power in order to bring everything back to the normal. As I mentioned earlier, one advantage of Tesla grid forming is that the power P and Q is dispatched in the power dispatcher, which means that the angle of the machine is initialized to 0, unlike other grid forming methods, which means that if you look at the load angle, power angle stability curve, if you initialize the load angle close to 0, based on the area equivalent point, you will have more limit before your synchronous generator or grid forming goes out of sync. At the graph at the top, you can see the response of a synchronous generator or a traditional grid forming where the power command is not 0, therefore the load angle is not 0, and you have to clear the fault before you go out of sync. But in the Tesla approach, since you have more room for the transient stability, you can have the fault stay there longer before you lose the synchronism within the machine.
Hey, good morning, everyone. I'm Sarah Walinga. I lead utility scale site controls at Tesla. I'm going to talk about some projects that we have, some lessons learned. I guess first, what is site controls? We calculate what the expected behavior is at the POI, design and implement all of those functions, and then we also take that expected value and command all of the individual batteries with the PQVF that you saw, also accounting for the impedances in the facility and the site level goals and limits. So we do have a lot of utility scale grid forming experience. I have some projects here, a lot in Australia. I'll highlight 2 in the US, KIUC, likely one of the first transmission connected grid forming projects in the world. And also Kapolei energy storage on the island of Oahu. It's 185 megawatts. Peak load of Oahu is 1,100 megawatts. So compared to the peak load, it's over 15%. So there's a real impact of this project and it has to behave as expected. We're not so good at publishing our accomplishments, but I think we also have one of the largest black starts in the world. This facility did black start all 185 megawatts, and it operates in grid forming all the time. At the end, I'll show a plot of the response of this facility to a grid event. Okay, so I'm going to talk through 3 lessons learned. These are very simple lessons learned. I'm not going to have one cool trick for current limiting or anything like that. These are going to be basic things that we can all ask questions and implement, and real lessons that we've learned as we've commissioned these really cool grid forming projects. So the first lesson learned is controls testing to ensure no surprises. We have a lot of test setups at Tesla. We have a lot of hardware in the loop setups at Tesla, and those hardware in the loop setups contain our Tesla system controller, which commands all the packs, our inverters, the meter that we use, and also we have our hill simulator, Typhoon. And why this is so important is it's not just the Tesla equipment on site in these facilities. We have RTACs with control equipment, other SCADA boxes, and those all have to play well together when contingencies happen. So with our hill testers, we can do regression testing. We use the testers for development. So if I'm building a new feature, I get to test that it works on weak grid, works with all the communication delays in the facility before it is even deployed to a site. And then lastly, we use it for site-specific testing, like I just mentioned. If we want to bring in an RTAC with a third-party code or controls, we can test that not only are the points mapped correctly, but that edge case behavior, which I'll talk about next, is also good, and we're not discovering anything bad on site. All right, the edge case behaviors also really matter. Probably 90% of my time working on site controls is spent on edge case behavior, not nominal power behavior, but what happens when there's an MIA, what happens if a device reboots, what happens if our controller loses power. And these edge cases are so important. So in this plot, I have here an example of a meter failure. So anything could happen. The meter could be MIA, maybe there's a PT failure, and we have defined responses for those events. In this example, once that meter failure is qualified, the plant in this case was configured to ramp down in a defined time interval. So both P and Q reach 0 at the same time. And talking about chill testing, these edge case behaviors matter a lot too with third-party devices, and on facilities, they might not always get tested together before they're deployed to site. All right, last lesson learned, model and plant benchmarking achieves expected behavior. So I think this is a common theme that people are talking about right now, that benchmarking of actual plant behavior versus the plant needs to be happening to make sure that everything is configured correctly. So I have a plot here of a frequency disturbance in Australia from a benchmarking report. Black is the expected PSCAD model value. Blue is the actual plant performance, and you can see that they match pretty perfectly. So we know that this plant was configured correctly. And I guess the GFM twist I'd like to say is oftentimes on these periodic checks, customers, utilities, they might like to stage the test. So what that means is maybe overriding a frequency measurement on the meter, and that can be problematic for a couple of reasons. One, we actually had a case recently where there was a PT phase rotation issue on the meter, and it was just constantly outputting 60 hertz. So if you stage a test, you're not going to catch those kinds of equipment issues. And then also with grid forming, it can be really hard to get a grid frequency measurement to all of the devices on the site simultaneously. So more and more, instead of checking compliance of facilities with stage tests periodically, we should really be looking at grid disturbances, giving some period of time and checking that the behavior was correct. Okay, last thing I'll leave you with from Tesla. So I talked about that Kapolei energy storage project on Oahu earlier. This operates in grid forming all the time. We have a machine in how our inverter is operating in grid forming. So in February of 2024, there was a 208 megawatt power plant that tripped offline, which you can see at 1 where the frequency starts to decay. The frequency decays, you can see the nice rate of change of frequency response of the grid forming inverters. And then HECO had actually configured the plant to also have fast frequency response, which when frequency hits a certain threshold, they set it up to command a power step. And you can see that happened at 3. So as soon as the grid hit 59.4, the facility injected an additional power step. And then from there, the frequency could start recovering. So we're very proud of this facility and the role that it's playing in the Oahu grid.
Thank you. Our next speaker is Deepak Ramasubramanian, who's from EPRI. I don't know what your title is. Hang on. Senior Technical Leader.
Okay. Great. Depending upon how I present, there may be a quiz at the end, okay? So just heads up. It all depends on me, of course. If I make a goof of it, that quiz won't be there. So I'm going to talk about benefits of advanced grid support in stability constrained areas of grids. And presentation is going to go along a few different examples that we have worked with our various members. And then also talk about a little bit of a conceptual aspect. I think Hossein touched upon it a little bit in his presentation, but it'll go into a little bit more details here. So how do we define what is advanced grid support from these inverter-based resources? We look at 3 different criteria for advanced grid support. We essentially have a time domain criteria, which looks at voltage and frequency control being prioritized in the subtransient and transient timescales. What this allows us to identify and look at is how really an inverter with advanced grid support versus an inverter without advanced grid support, how do they compare against each other for things as simple as a voltage step test, frequency step test. My sincere request to all of you is whenever y'all are talking to other parties who are involved, so OEMs, developers, GEOs, system operators, planners, study experts, everybody in that cycle, always ask this question. How does the device that is being talked about, how does the resource that is being talked about, the resource being studied, how does it respond to a voltage step? How does it respond to a frequency step? Now, it's not meant to be judging. It's not meant to be as a comparison. It's more as just an easy way to get an understanding of how does this device respond. Then going away from time domain, because in time domain, you look at one snapshot, you look at one point in time, one instant, one operating point, one scenario, we go to frequency domain. So in a device that provides this advanced grid support in frequency domain, we expect it to have a near constant gain. So especially if you look at the voltage to reactive power. So change in voltage to change in reactive power have a near constant gain in a certain frequency range, and it has a phase angle closer to 180 degrees. What this essentially means is if voltage drops, reactive power will increase. Voltage rises, reactive power will reduce. And you can see this for a wide variety of frequency events that might occur. So this showcases network support functionality in frequency domain. But just these 2 are not enough to characterize a device that provides this advanced grid support. You need to have a stabilization aspect. You need to have an aspect that it can work to improve damping in the system. You need to have an aspect that it can work to improve the stability in the system. So there is a stability and robustness property that comes in. So this is, you look at the active power to frequency of the device. You look at that characterization. And here is where it depends upon the device. So the reason why a specific value of frequency is not mentioned there is it can change depending upon whether this is a battery, whether this is a wind turbine, whether it's type 3 wind, type 4 wind. This cutoff frequency will depend upon all of those conditions. It will depend upon whether the battery is a 10 megawatt battery versus a 20 megawatt battery versus a 50 megawatt battery versus a 100 megawatt battery. It will depend upon whether the 100 megawatt battery is operating at 1 per unit, 0.9 per unit, 0.8 per unit, 0.7 per unit. It depends on all of that, because this relates to at that given operating point for that particular device, for that size of the device, how much damping can it provide to the system? How much stabilization can it provide to the system? How much robustness can it provide to the system? And then you have a phase angle criteria on it. Above that phase angle or above that frequency cutoff, we want it to have low gain. What that essentially means is if there is an oscillation in the system, it doesn't have to react to it. So this provides a stabilization and robustness property in frequency domain. If you want to know more about the technical gory details and all the work that's going on at EPRI, SIG, Unify, and other places about this, catch me at the breaks and I'll be happy to show you all plots and go down into the math of it. The takeaway from all of this is that the exact control structure of an inverter does not matter when defining whether it's providing this advanced grid support or not. what control elements the OEM chooses to use, the way in which they structure their control elements, the way in which they prioritize their control elements, the way in which they make their control elements talk to each other, at what point in time the control element comes into play, what is its tuning, all of that doesn't matter. When you look at the control structure, look at a block diagram, nothing about that block diagram will tell you about whether a device can provide this advanced grid support or not. So another request there is when you're trying to characterize inverter-based resources as to whether it can provide support or not provide support to the system, can be helpful, not be helpful to the system. The control structure is important, but don't base decisions based on that. Okay, so now let's look at some examples. The first example, we're going to look at a case study that we did on helping deploy this advanced grid support inverter in a region that had a stability constraint, and we wanted to relieve that stability constraint. This is part of a larger grid. There are different locations where there are inverter-based resources connected here, and there are prior outages. So there is the dashed lines show a prior outage that is there, and then one of them could be a prior outage, one of them could be an actual outage that happens at that point in time. And then there is a restricted constraint path for the wind and solar farms in that area in order to provide the power injection into the network. And because of that, you had these kind of instability events that came up. And by finding out the location where to place this advanced grid support inverter, we were able to identify that, okay, now you can stabilize the system by placing this. Hossein touched upon this a little bit in his presentation. It's extremely important to know where to place this device, this advanced grid support inverter, especially if this is an existing area of the system that has already a constrained nature. So these resources, these existing inverters might be constrained because of a stability limit and so on. And if you want to alleviate that stability constraint, you cannot place this advanced grid support inverter anywhere in the network. You have to really identify and locate a scenario or a location or a bus where it can provide the maximum benefit to the grid. So you're able to do that, and then you see that, okay, this can help the network. But that leads to a secondary question. Okay, how do we get these devices into the network? We're talking a lot about interconnection queues nowadays in the industry. We're talking about how there are so many batteries in the interconnection queue. Why don't we get these batteries with advanced grid support? And they're going to do well for the system, hopefully. But what if that location where the battery is connecting into the interconnection queue does nothing good for the network? You might bring in all this advanced grid support, but it may not help the network at all if there is a constraint already in place. So being able to locate where this device has to go is critical, is important. And there are ways to do that. There are ways to identify that. So we did another evaluation with some of our members where this is a larger portion of the Eastern Interconnect, and there is this pocket in this larger portion of the Eastern Interconnect. And there are a bunch of wind plants, and there is a stability constraint in place. There is a scenario where if a fault occurs with prior outages, you're going to have, again, instability effect come up. And there are batteries in the interconnection queue in this broader region. So the idea was to try to identify, okay, can these batteries that are in the interconnection queue, if they are enabled with advanced grid support, really help this region or not? Because if they can't, then that battery is not going to be helpful, and some other solution needs to be found out for this particular region of the network. So we did a bunch of screening, and the study is actually still ongoing. So hopefully by October, we might have more results to share in the next workshop. But we were able to find out that there are certain locations, depending upon some screening metrics to use, depending upon system strength metrics, depending upon interaction factor metrics, depending upon system support metrics, that you can do a quick evaluation and find out if those particular constraint regions are really going to be benefited by the batteries that are connecting at their point of interconnection at the location. The takeaway, though, from here is that just adding a resource to this advanced grid support may not necessarily help the system. It needs to be targeted, especially if looking to alleviate a critical aspect or a critical contingency or a constraint that is already in place. it may not really help, and so we need to find out where to put it. The next study that we'll talk about goes a little bit more into the research and analysis realm, where it touches upon something that Hossein mentioned on subsynchronous resonance and damping. So can these resources really provide this much of damping? Especially if you have a scenario where you have some wind in place and you have some series compensated lines, and then you have contingencies that occur that might make the wind be radial with the series compensation, triggers an oscillation. Can you bring in advanced support inverter into that system? We're not talking about replacing. So we're not talking about taking the wind plant out and replacing it with inverter-based resource with advanced support. We're talking about that system stays in place. Can you bring in a new advanced support device and damp the oscillations out? So we've seen that if you just compare one particular OEM, and this applies to a lot of the OEMs by commonality, you can see that if you don't have any advanced support control enabled within the device, then you have over a frequency range, you have more negative resistance coming up, which indicates that this particular device without the advanced support may not be able to help the network much. At critical resonant frequencies, it might actually introduce more negative damping, more oscillations, and so on. But if you have advanced grid support enabled, then you see the orange and the green curve, that resistance value becomes more positive. It becomes closer towards the 0, and it actually has a vast improvement with respect to without having that advanced grid support. So this itself might give a impression that this is going to have an impact on the system. It's going to have improved damping. It's going to bring in all of this good behavior into the network. Not necessarily so. So if you look at a scenario where we have a test network that has some synchronous machines, or indicated by the black circles, you have a series compensated line, you have a type 3 wind resource, you have some full converter resources, all color coded there. And if you actually trigger a contingency wherein you take out that line marked by the cross, you see that the green, which is the type 3 wind, becomes radially connected to the series compensation, and that triggers an oscillation. So we decided that, okay, let's find out the ability of an advanced grid support inverter helping out the system if it comes and connects at the location marked in orange, close enough to the compensation, not at the same bus, not at the same POI as the wind plant, because this is a whole different OEM, a whole different geo coming in. They don't want to connect at the same POI. The type 3 wind resource does not want to become a hybrid plant. So that's out of the question. We want to see now if this battery, which has this advanced grid support coming in, is really going to help this network or not, because we saw that if it has advanced grid support, it's going to have lesser resistance. It's going to be able to provide more damping. So let's see what happens. What you see is the lower figure shows the crossover frequency where when viewed from the type 3 wind. So the type 3 wind is looking into the network. It sees the series compensation. You see a crossover frequency of the impedance occurring roughly at 46 Hertz. That's where the resonant mode occurs. And with the advanced grid support, you see that actually now in the network, the resistance that the type 3 wind sees has reduced. Without that battery being there, the resistance was more. So adding that battery with advanced grid support actually reduced the resistance in the network. So what this means is that the presence of an inverter with advanced grid support capability at this location can actually lower the damping in the network. That is, without the battery versus with the battery with advanced grid support. There is, of course, the other option that is there, which we'll talk about it. But just the placement of this battery with advanced grid support, even though when you look at it by itself, it shows a much better resistance characteristic, what the type 3 wind is seeing is it potentially sees a lower resistance, which means that the oscillation could be much more. The impact of the resonance could be much more, and that's precisely what we see. We see instability cropping up in the orange curve. It's a bifurcation cropping up that happens with the advanced grid support coming in. Now, the third option that we spoke about is, of course, the first option is without battery. Second option is with battery with advanced grid support. Third option is with battery without advanced grid support. And here is how it looks like. There is a little bit of difference, especially what the type 3 wind is seeing. There's a little bit of difference in what the type 3 wind sees when you have battery without advanced grid support and battery with advanced grid support. But it's not necessarily going to always improve damping. So just to keep this in mind, it goes back to the core question of where to locate, where to place, where to size these kind of resources. And keep that always in your mind, that exact type of control architecture is not important. Performance can be provided and improved in local pockets, but it's very important where you place it, because even though a resource by itself might show an improvement in characteristic, it's not guaranteed when it connects to the network, you're going to have an improved performance and improved characteristic, improved behavior. And with that, Unruh, done.
Thank you, Deepak. Our last but not least presenter is Mohammed El-Nozahi, engineering manager from IESO in Canada. Welcome.
Good morning, everybody. It's a pleasure to be here presenting to you. So today I will be deviating away from the simulation results and plots, and I will dive more into how ISOs are looking at GFM, or at least how the ISO is looking at the GFM. So before I start, I will just give a brief background about our system in Ontario. We are part of the Eastern Interconnection. We have 3 voltage levels. We are connected to our neighbors with the famous ties that I'm sure everybody heard about. And yeah, they are divided into 10 geographical zones. And like we have extensive long network, our peak demand is 27 gigs, not as big as other jurisdictions. But when we look at this slide, this is the current installed capacity in Ontario. And as you can see, we are mostly a synchronous-based jurisdiction. Like we have 14% wind, 7% solar, but if you consider the capacity factor, the power penetration is much less than that. We still have lots of nuclear. Hydro is the majority of our fleet. And we have growing storage penetration. However, this is changing in the future. We have one of our 3 nuclear units, Pickering, is retiring soon. So we are having much lower inertia in the future. If you look at this, this is our EPO. For somehow like you see that we are losing capacity. And at the same time, I didn't show that slide, but our demand is growing. Our demand is expected to grow from 28 up to 42 gigawatts by 2035 due to all the electrification initiatives. So the landscape is changing basically. So now we are having reduced supply, increased demand, and we have plans basically. And as everybody know, like the timelines to construct new gas is expanding. So we are focusing more in renewables. So our efforts, we are doing 3 procurement efforts, expedited LT, that was done almost like we did all the studies for that, and we started commissioning some of the plants, 1.2 gig. Overall, we are expecting to add close to 6.6. This number has been revised by 2031. So 6.6, that's not a big number, but if you look at the percentage of our peak demand, that's significant. That's like more than 20% of our installed capacity, and that's coming over the next 6 years. So that's the challenge we are having. So today's approach. So at the ISO, okay, like grid forming is adding a lot of benefits to the network. Grid forming, they provide stability, better performance, better control. But when I first joined the ISO in 2017, I heard the exact same thing about GFL. Everyone was saying that these are the next big thing. They will fix all the problems. And only after we started installing them, we started seeing all the problems. GFM, they have a great potential. I agree with that. But if you don't use it properly, like Deepak mentioned in his presentation, they can actually make things worse. But at the same time, we cannot continue with the GFL where we are right now. So what's the approach we are doing? So the approach we are doing basically like towards wait and see, but don't just wait and do nothing. So our landscape is changing. GFM is promising technology. We are positioning ourselves for the future. Right now, we have a relatively strong grid, at least for now. When we are doing our assessment for GFL, for the inverters, our worst case short circuit ratio that we are assuming is short circuit ratio is 3, which is for other jurisdictions is considered pretty good short circuit ratio. So for now, at Ontario, at least, we have the luxury of waiting, but not waiting passively, doing nothing. We are proactively preparing for the future. And how is that? So again, the other way we see it, most of the loads that are growing, similar to all other jurisdictions, they are data centers, hydrogen facilities, tons of arc furnaces, and most of these are active loads. So in the past, we have a landscape where we had active generation feeding passive loads. But in the future, we're having more active generation feeding more active load. So the entire landscape is changing. So we need the flexibility, and GFM is providing good flexibility. So now I'm providing two contradictory messages. We are doing nothing, but at the same time, we need the flexibility. No, we are actually positioning ourselves for the future. So what we are doing right now, for all the projects we are adding, for all the storage, we are mandating GFM capability. We are not enabling it, but, and sorry if I go back, we are focusing on storage, BSS, because as everybody know, this is the low-hanging fruit. It's mostly a software modification. And out of our 6.6 gigawatt target, I think more than 3 gigawatt of that are storage. We are not in need to enable that GFM right now. I'm sorry, I know this is not the message that everyone expected. Everyone is expected, we are doing this, we are adding that. But in my opinion, the electric grid is not a simulation bed. Like you can get all the results you want in the simulation, but when it comes to enabling something in the grid, we have to be cautious. But again, not to sit doing nothing, position ourselves for the future. So for all the projects right now, we are mandating GFM capability. And we are doing our validation as if we are enabling the GFM capability based on the best available knowledge we have today. But as everybody know, this knowledge is progressing every day. Oops, sorry. There we go. So before formulating our market rules, again, this is boring part of my presentation, but we have to operate within the regulatory framework we have at the ISO, within the market rules. We don't have the luxury to go to OEMs or developers and just mandate something. It doesn't work like that. So in our models, in our market rules, in our performance requirements, we specify dynamic, not phasor domain or not EMT. We require dynamic models. And our interpretation of that, dynamic models, they include PSSE models or like positive sequence model, and they also include EMT models. So that's the legal framework we are operating from. Also, we are requiring GFM capability. And like this almost like took us months back and forth with our lawyers. Do we require the capability or the provision? And for other eyes in the room, like provision, basically you have, in principle, the equipment can support GFM. But the capability, it means that it's right now, it can support GFM with a minor setting change. And that's what we are requesting. We are not requesting them, like we can request wind and solar to have the provision that in principle, they can operate in grid forming, but they will require some storage added to them to have the capability. So we are taking a step further. We are requiring all of them to have the capability. And we are assessing all the projects. We have model quality testing benchmark. So we run like automated tests to do the model quality testing. We do it ourselves in-house at the IESO. We run more than, I would say, 700 tests for each IBR, testing at different operating points, different configurations. And in that, we include GFM performance. We include the best known performance at the time. The other thing, we are not getting GFM completely out of the picture. Like in some projects, we considered implementing GFM because, again, in general, our grid is strong, but grid strength is relative where you put the, so if you don't position your IPR in the right location, you may end up in a situation where you need the GFM. So we assess that on project by project basis. We had one project, we were like almost considering installing a GFM. The short circuit ratio was 2.2, but we tested the battery and we worked with the OEM and they were able to provide a stable response using the GFL at the POI for 1.8. So we could do GFM. We were more than willing to go for GFM, but we are not enabling GFM just for the sake of enabling GFM. Like we are more pragmatic in our approach. The challenge we are facing, so like there's lots of work on that, but apart from ERCOT, EMO, and some work at MISO, I haven't seen NERC standards for GFM specifications, for GFM testing. Yeah, we can adopt the best of every world, but again, we need, like, we don't update our market rules once every year. So basically, we need some agreed upon. The other thing that not many people are talking about, so now we have parallel effort to implement P2800. How does GFM play with P2800s? Because MISO, they did a very nice work and they showed that actually GFM will need some exemption for some of the provisions of P2800s. So do we implement P2800 and then contradict ourselves by mandating GFM? Again, these are some questions that the industry need to work on before we start enabling it. Yeah, 2 more slides. So these are our general requirements. The main word here is capability. So we require the capability for all the projects going forwards. And what are we doing right now? We are basically like cooperating with the industry. We are reviewing best practices, doing a lot of stakeholder engagements with OEMs. Like Tesla, they are visiting the IESO. We do, like, we have dialogue with the consultants, with other ISOs. We are actually part of our Grid Innovation Fund, which is $8 million every year. We are having some, we are considering the theme of using GFM, but we haven't, do we do a pilot project? Do we do like, so we are looking at enabling it as part of research. We are funding active research at University of Toronto. And right now for our requirements for the GFM, we are adopting the most agreed upon NERC definition, which is to maintain constant or near constant internal voltage phasor and be able to synchronize and regulate active and reactive power. When there are more agreed upon definition, we would definitely be the first to implement it. We are working with ESEG, with all the working groups, trying to reach that consensus. Again, I mentioned that we are using our model quality testing framework to test all the projects as if we are enabling GFM. So that literally for all the projects we installed, we can enable GFM within 3 days because we have all the tests ready. We did some studies with GFM, but again, again, future considerations, doing more research, development, continue collaboration, learn, learn, learn. That's the magic word we have. The challenge, like balancing proactive measures with our low urgency due to the string grid conditions for the time being. And the opportunities, yeah, like I mentioned, we have change in our landscape, 20% IBR penetration expected very soon. So we have to position ourselves well for the future. Yeah, so our proactive approach, although not, I would say it's not the ideal approach for the time being. I think it's pragmatic. It works well for our needs. Every ISO should look at its network and determine the approach that suits them best. That doesn't mean that we're not doing anything. We started our EMT like journey 2 years ago. Now, last week, we got like one of the largest scale EMT models in the world. So it's like we are working, we are being proactive, we are like preparing ourselves for the future, but we are not taking, wouldn't call it risks, but I wouldn't enable GFM again or any technology just for the sake of enabling it. And yeah, that's my presentation. Thank you, everybody.